Lesson 10.3, page 560, Solving Radical Equations. In this lesson, you will learn how to solve a radical equation, how to identify extraneous solutions from radical equations, and how to solve a real-life problem involving a radical equation. So let's talk about solving a radical equation. There's a certain way we have to do these. A radical equation is an equation that contains a radical expression with a variable in the radicand. To solve a radical equation involving a square root, first use properties of equality to isolate the radical on one side of the equation. So what I have in purple here, that might sound complicated, but it's really saying something very simple that I've taught you all year. This is very similar to what we did in lesson 9.3 when you had problems with squares. This is saying get the radical by itself first. So you have to onion the radical. So that in purple, it's telling you isolate the radical on one side, get everything else on the other. The next step then is to use the following property to eliminate the radical and solve for the variable. This property is called squaring each side of an equation. So if you have a square root isolated, this is saying you can square both sides of a problem and it still stays equal. So the inverse of a square is a square root, and the inverse of a square root is a square. I think it might be easier to show you a couple examples of what this property is telling you. So let's see that at work. So let's solve each of these equations. So the first equation, square root of x plus 5 equals 13. First step, take away 5 from each side because I have to get the radical by itself. So when I do that, I get square root x on the left and 13 minus 5 is 8 on the right. Now that the radical's isolated, do you notice what they're doing here? They are squaring both sides of the problem. A square and square root cancel, so I have x on the left and 8 squared 64 on the right. The answer would be x is 64. Here's another problem. 3 minus square root x equals 0. The book decided to add radical x to each side to get the radical all alone on the right, and you have 3 on the left. Now you can square each side because a square eliminates a square root, and you have x on the right and 3 squared is 9 on the left. You have x equals 9. So it's pretty easy to use that property. Isolate the radical, square each side, and you've solved the problem. What I'd like you to do is pause the video and do questions 1 to 4. Make sure you show work because I would, like on a quiz, I would want to see the work for these. So go ahead and do that. And I'm back, and these should have been the solutions and the work you had for these. So you notice on each question, I'm isolating the radical. I am then squaring each side to get my response. Sometimes radicals might have more than just x or variable underneath the radical. Like here you can see we have the radical x plus 2. No big deal. Just make sure you isolate the radical. So think onion. Let me draw onion rings on this. Okay, here's the center of the onion. The 4 is the next layer, and the 3 is the outside layer. So to solve this, I would have to take away 3 from each side first. That would give me 4 times radical x plus 2 equals 16. Then I would divide each side by 4, and that would give me radical x plus 2 equals 4. Now I can square each side of the problem. And a square eliminates a square root. I'd have x plus 2 on the left and 4 squared 16 on the right. And now I can take away 2, and x would be 14. If you have radicals on both sides of the equation, that's not a big deal. Each side has a radical. All you need to do is square each side of the problem. And you can see that here. They're squaring each side of the problem. So square eliminates square root. I have 2x minus 1 on the left. Square eliminates square root. I have x plus 4 on the right. Now I got to solve this. So they didn't really show the work. Let me just put it up here, make sure we're all on the same page. So take away x, and I'd have x minus 1 equals 4, and then I can add 1, and that's why x equals 5, and you can see that here, okay? There is another way you could solve this without work. You could use your graphing calculator and the intersect feature to solve these. The only problem with that, it's not a work method. On my quizzes, I will definitely ask to see the work, but just to review that, this is what you'd do. You'd make y equal to radical 2x minus 1, and then you'd make y equal to radical x plus 4. You'd type that into your calculator, and you'd hit graph and use the intersect feature, and you would be able to find the answer. They're showing you a picture of it here, okay? So you could really do that method also. The only problem with that is that's not a work method, and every quiz I give you, I'm going to demand the work if you want to get an A for it, okay? So keep that in mind. You will also be asked to solve radical equations that involve a cube root. That's not a big deal. The only difference is I have a little note here. You'll see it. Instead of squaring each side, if you have a cube root, you got to cube each side to eliminate the radical. So look at the sample. The cube root of 5x minus 2 equals 12. You notice how the radical is isolated. That's the first step. You always make sure your radical's isolated. Now, to get rid of a cube root, you cube each side. And you can see they're doing that here. They're third powering each side of the problem. The cube will eliminate the cube root, so I have 5x minus 12 on the left, and if you take 12 to the third power in your calculator, you get 1,728 on the right, and they didn't show their work again. Let me write it up here. We need to add 2 to each side first, so 5x would equal 1,730, and then I'll divide by 5, and that's why they're getting the x equals 346. What I'd like you to do is pause the video, and why don't you try 6, 8, and 10. Pause the video, make sure you show your work. And I'm back, and here's my work for 6, 8, 10. And I thought what might be good to do just to show you, I'm going to do one with my calculator in the intersect feature just to show you it works. You can see my work for 16 and 6, I meant to say, and the answer is 30. Let me put this in my calculator and show you that I'm also going to get 30 by doing that. Here's how I would do it. I would make y equal to 15, and I would make y equal to 6 plus radical 3w minus 9, and I'd use the intersect feature. So let me show you that. Okay, so you can see I typed y equals 15 and y equals 6 plus square root 3x minus 9 in my calculator. I'm going to use the intersect feature, so I'm going to do second trace intersect, and you notice I'm not seeing both lines meeting, so I better zoom out. I'm going to hit the zoom button, and I'm going to zoom out. Press enter once. Okay, let's see if I can see the intersection now, and yes, I can. You can see over here I'm pointing at it. There's my intersection. So let's go back to the trace feature again, second trace, and we're going to intersect. And my cursor's on the first line, good. I'm just trying to find, okay, yep, there's my cursor. It's on the second curve. And I got to move this cursor. It looks like about right there is where they meet. So there's my guess. Press enter, and you can see it right here. It says the answer's 30 for x, just like I had in my written work. So this feature works nice for this also. Here's the only bad thing. This method does not show work. So for multiple choice questions or gridded answer on a test, you could use this. On my quizzes and tests, you can't because you could, you just can't get full credit if you don't have your work. Now, when you solve radical equations, they can produce extraneous solutions. We learned about extraneous solutions way back in chapter 1, lesson 4 earlier in the year with absolute value equations. Remember, an extraneous solution is when you show all your work correctly and it's giving you an answer, but when you check the answer, it doesn't actually work. So it's like a false solution. When you solve radical equations, you could get an extraneous solution, so you have to check these, okay? So here would be an example problem that would have an extraneous solution. Let's solve x equals square root of x plus 6. So you notice the radical's isolated, So we need to square each side of the problem. So they're doing that. You can see that here. Square eliminates square root. And on the other side, when you take x squared, you have x squared. Oh, I have a quadratic. So maybe I should make a little note here. The only time you can get an extraneous solution is if the problem develops into a quadratic. So you might want to put that notes. Quadratics can have extraneous solutions. Quadratics can have an extraneous solution. Okay, so I'm going to put everything on one side, 0 on the other. I took away x, took away 6 from both sides, and I get x squared minus x minus 6 equals 0. You know I like factoring, and this factor is nice because doesn't negative 3 times 2 give me negative 6, and negative 3 plus 2 give me negative 1? So there's my factoring. So I get two solutions. If I use positive 3, that's an answer, or negative 2. Now let's check it. If I put 3 in here, I get 3 on the left, and 3 plus 6 is 9, and the square root of 9 is 3. So 3 checks. Now let's try negative 2. If I put negative 2 in here, negative 2 plus 6 is 4, and the square root of 4 is 2, but over here I get negative 2. Okay? This would produce an extraneous solution. It's important to understand when you work with solving radical equations, we're only using the positive roots when you take the square root. So I'm getting negative 2 on the left, but positive 2 on the right. That's extraneous. Okay? So negative 2 would be an extraneous solution. All the work was correct, but the answer's still not. Here's another sample problem with an extraneous solution. You notice we have to isolate the radical first. So I'm going to go ahead and take away 13 first. I have to isolate my radical. You can see I'm doing that here. Subtract 13, subtract 13. So I'll get radical 5n is equal to negative 10. So I should square each side. You can see I'm doing that here. So square cancels square root. 5n would equal negative 10 squared is 100. And I divide by 5, and I'm getting 20. Okay, let's check it. Let's plug 20 back up here. I would have 13 plus square root 5 times 20 is 100 equals 3. This turns into 13 plus square root of 100 is 10. Now think, does 13 plus 10 give me 3? No. Okay, so I know that 20 is extraneous. Okay, so I guess I got to take back something I said. Quadratics typically will give you extraneous solutions. I guess this is not a quadratic, and I could still get an extraneous solution. So I guess we got to check all the radical equations, because even if it's not a quadratic, I just showed here, we could get an extraneous solution. Okay? If it's a quadratic, you typically definitely get an extraneous solution in quadratics. So maybe I should rephrase that. I'm going to write it down here. So that would probably be a better way of saying it right here. Quadratics typically produce extraneous solutions. Typically means normally, but not all the time. But you're going to need to check all radical equations, because this was not a quadratic, and it still produced an extraneous solution. Okay, what I'd like you to do is pause the video. You try 11 and 13. And I'm back, and here's my work for 11 and 13, and in each of these, it produced two solutions, one that checked out and the other one was extraneous. So this is what you should have worked it out to, and you're noticing in each one of these I get an extraneous solution. To wrap up the video, you would be solving in this lesson real-life problems that could use radical equations. Like here you see a problem where it says the period of a pendulum is given by this function, where L is the pendulum length. You notice this function has a radical in it. The pendulum has a period of 4 seconds. Is this pendulum twice as long as the pendulum with a period of 2 seconds? So the variable P stands for the period. So they're giving us two different scenarios, one with 4 seconds for P and one with 2 seconds. You notice, here's the equation for a pendulum with a 2-second period, and here's an equation for the period of 4 seconds. So first thing, let's isolate our radical. So you notice they're saying divide each side by 2 pi. Let me highlight the 2 pi's. You notice how we have 2 pi here and here. If we divide both sides by 2 pi, we will eliminate 2 pi from being next to the radical. So that's the first step. Get rid of that 2 pi. Okay? So now we have 2 over 2 pi equals radical L over 32, and 4 over 2 pi equals radical L over 32. Okay? The book then simplified. 2 divided by 2 is 1. That's why they now have 1 over pi is equal to the radical L over 32. And over here, 4 divided by 2 is 2. We have 2 over pi radical L over 32. We got to square each side to get rid of the radical. So when you square over on the right, that means the radical disappears. And when you square on the left, you're going to get 4 over pi squared here. And if you square here, you're going to get 1 over pi squared. And then the next thing is to get rid of divide by 32, you can multiply both sides by 32. So the answer to this problem would be 32 times 1 over pi squared. That would give you about 3.24. And over here, when you multiply each side by 32, cancel here, L would equal 32 times 4 over pi squared. That's about 12.97. Now the question is the pendulum twice as long? Well, you look at it, no, it's way more than twice as long. 12.97 divided by 3.24 is about 4 times longer, okay? So anyway, you could have word problems that have radicals in them is the point of this last part. I'm going to pause the video here. If you have any questions, make sure you ask in class.